All right, so now that we understand rotational kinetic energy, it's time to come back to this example that we saw earlier of when we release a bunch of objects from rest at the top of an inclined plane. A spherical shell, a solid sphere, a cylindrical shell, a solid cylinder, and a frictionless cube. They each reach the bottom of the inclined plane at different speeds and at different times. And now we have enough information to understand why this is happening. We just derived the equation for the velocity of a solid sphere at the bottom of an inclined plane using the moment of inertia as 2/5 mr squared. If you were to repeat this process for each of these objects using their respective moment of inertia equations and deriving an equation for the velocity of these objects linearly at the bottom of the inclined plane, you would get something like this. All right, and so I can tell here by looking at these velocity equations, but also at the diagram, the frictionless cube comes in first place. It has the greatest equation here for velocity, that 2 is the biggest number. The solid sphere comes in second place, it's got 10/7 here. And remember, the bigger the number in the square root, then the bigger the velocity is going to be, right? In third place, the solid cylinder, 4/3 here. Fourth place, we've got the spherical shell at 6/5. And then lastly, we have this cylindrical shell, which just has a 1 right here. So the smallest velocity belongs to the cylindrical shell. And what we see is that that aligns well with the position that each of them finished in. Now, let's see how that compares to each object's moment of inertia, and hopefully we'll see an interesting pattern here, right? I noticed that the cylindrical shell has the lowest velocity, but it has the greatest moment of inertia, right? The moment of inertia, the constant here is a 1 next to the cylindrical shell. And if you look at every other moment of inertia equation, there's a number less than 1 in front of the mr squared. And so the cylindrical shell, while it has the slowest velocity, has the greatest moment of inertia, right? If I go to my second place finisher here, the solid sphere, I would see here that it has the lowest moment of inertia. The cube, in this case, isn't rotating at all. And so that one actually ends up being the best, right? Because all of the potential energy of the cube went directly into translational motion. None of it became rotational motion. But the solid sphere here had the smallest moment of inertia for those objects that were rotating and had the second best velocity. And so I'm noticing a pattern that looks like this. The greater the moment of inertia of an object, the lower or the slower the linear velocity of that object. And if we take a moment to go back to the formula for rotational kinetic energy, right, we would see why, right? The rotational kinetic energy of an object is I omega squared. Well, as I is increasing, right, as the moment of inertia is increasing, more and more of this energy, this rotational term is getting bigger, right? And so what's happening is, imagine they all start from the same point, right? So if we're going to draw a little LOL diagram here, I'll just draw a little bar chart. I have this gravitational potential energy, okay? And I have two places that can go. I have translational and I have rotational kinetic energy, okay? So the larger the moment of inertia, right? So the greater the moment of inertia, if I goes up, then the rotational kinetic energy is going to go up as well. And so the more energy is going to be taken by rotation. So the rotation will be higher, the translation will be smaller. What's happening is, as the moment of inertia of these objects increases, more of the energy is being used for rotation and less is being used for translation. And so because the frictionless cube has 0 rotational kinetic energy, it has maximum translational kinetic energy and reaches the bottom of the inclined plane first. On the other hand, the cylindrical shell has the greatest moment of inertia, and so it will have the greatest rotational kinetic energy, but the lowest translational kinetic energy. And this helps us explain why these objects reach the bottom of the inclined plane at different times. So this concludes our series of videos on rotational kinetic energy. Please take a look at Canvas for some additional practice problems to continue to apply your skills.